Okay, let's dive right into this. For the past couple of years, the entire AI world has basically been obsessed with scale, right? We're talking bigger parameter counts, massive data centers, and these sprawling models that seem to know a little bit about, well, everything. But right now, there's this incredibly quiet revolution happening just under the radar. We are seeing a massive structural shift away from those giant monolithic large language models towards something much more agile. We're talking about small language models. So today, we're going to unpack exactly why this shift is happening, the brilliant engineering that's actually making it possible, and how it's completely reshaping the future of agentic AI.
So here's our roadmap for the explainer today. First, the AI efficiency crisis. Second, defining small language models. Third, the science of compression. Fourth, advancing SLM tool use. And finally, building hybrid AI systems.
All right, part 1, the AI efficiency crisis, reevaluating the bigger is better myth.
For the longest time, the prevailing wisdom in AI was literally just bigger is better. But the industry is currently waking up to a fundamental mismatch. There's a massive gap between these gargantuan models we've built and the reality of the repetitive, highly scoped tasks that AI agents actually perform in production. Think about it like this. Would you ever hire a highly trained neurosurgeon just to take your blood pressure? Of course not. That's total overkill, it's insanely inefficient, and frankly, it's wildly expensive. But guys, that is exactly what the tech industry is doing right now. In an agentic workflow, most tasks are actually incredibly narrow. We're asking AI to classify a support ticket or pull a couple of specific fields from a JSON document. Throwing a 70 billion or 100 billion parameter model at those simple, scoped tasks is the computational equivalent of hiring that neurosurgeon to wrap a blood pressure cuff around your arm.
And the cost of this overkill? It's staggering. We're talking $57 billion. The industry has sunk an estimated $57 billion into LLM cloud infrastructure. That is a massive sunk cost. At an enterprise scale, where you might be dealing with millions of agent invocations every single day, running inference on these giant models is rapidly turning into a burning money pit. The math just simply doesn't work for sustainable business growth when every tiny, routine task is costing you a massive premium.
When you really break down the economics and the speed of LLMs versus SLMs, you realize they exist in completely different universes. For a frontier LLM, you're paying single to low double-digit dollars per million tokens, and you're sitting there waiting anywhere from 500 milliseconds to several seconds just for a response. But on the SLM side, we are talking cents, literally fractions of a cent if you self-host. And the latency is lightning fast, dipping down to 20 to 250 milliseconds. It's just a completely different operational reality.
Moving on to part 2, defining small language models, specifically looking at their capabilities under 15 billion parameters.
So what exactly makes a model small in 2026? A small language model, or SLM, typically sits somewhere in that 1 billion to 15 billion parameter range. We're looking at models like Google's Gemma 4, Alibaba's Qwen 3.5, or Microsoft's 5.4. And I really want to emphasize this. These are absolutely not toys. They are highly capable, incredibly fine-tunable, specialized machines. Because they're designed to run efficiently on consumer devices, on edge servers, or even just a single standard GPU, they offer real-time utility that massive LLMs physically cannot match without leaning on heavy cloud compute.
And they punch way above their weight class too, thanks to some brilliant architectural optimizations. Instead of using standard attention mechanisms that just totally hog your memory, they use sliding window attention to keep that latency ultra low. They utilize mixture of experts, or MOE, so rather than firing up the entire network, they only activate a tiny, specialized fraction of their parameters per token. And, surprisingly, they have massive context windows now. I mean, Gemma 4 is offering up to 256K tokens. Plus, they natively process video, image, and audio straight on device. Basically, they're giving you the premium features of an LLM, but packed inside a highly modular, hyper-efficient shell. Which brings us perfectly to part 3. The science of compression, how we actually physically shrink these models down. So how do engineers actually cram so much raw intelligence into such a tiny footprint? Well, the first and honestly the easiest technique to apply is called quantization. Think of this kind of like lowering the resolution of an image so it takes up less space on your hard drive, but, applied to math. By simply reducing the numerical precision of a model's weights, like shifting from a 16-bit format way down to 4-bit using methods like AWQ or GPTQ, we can slash the VRAM footprint by up to 75%. And the crazy part? The actual drop in response quality is practically invisible.
The next big technique is pruning.
Now, unlike quantization, which just sort of fuzzes the precision of the numbers, pruning permanently deletes structural components of the model itself. By using frameworks like sparse GPT, engineers can actually strip out entire attention heads or neurons that basically aren't pulling their weight. Because you're physically removing computation from the pipeline, this doesn't just save memory, it gives you real, tangible inference speedups of anywhere from 10 to 50% on standard hardware.
The third, and arguably the most powerful technique, is knowledge distillation. This is where we take a massive teacher model and use it to train a much smaller student model. But instead of just handing the student the final correct answer, the teacher model actually shares its entire thought process, its full range of output probabilities. That richer level of supervision allows the small model to genuinely mimic the reasoning capabilities of its giant counterpart. Now, it's the most expensive technique up front because you do have to train that student model, but it undeniably produces the highest quality small models out there, like Distilberg and the Phi 3 Mini.
Now, what's absolutely wild is the 40x multiplier we see in recent research. Take the Nematron 4 model family, for example. Researchers found that by stacking these techniques together, specifically pruning an existing model and then using distillation-based retraining, they were able to compress a 15 billion parameter model all the way down to 8 billion and even 4 billion parameters. And doing it this hybrid way required 40 times fewer training tokens than if they had just tried to train those smaller models from scratch. I mean, that is just a massive, game-changing leap in training efficiency.
So, summing up the trade-offs here, quantization gives you a massive memory reduction for very little effort and incredibly low quality loss. Pruning gives you a true speed-up by permanently removing parameters, with maybe a 1 to 3% degradation. And distillation gives you the absolute smallest footprint while maintaining the highest quality, though it does require upfront training. But here's the secret. In a real production pipeline today, engineers don't just pick one. They use all of them. They'll distill a massive model down into a smaller one. They'll prune its unnecessary heads, and finally they'll quantize it so it runs beautifully on a single, super affordable GPU.
All right, let's look at part 4, Advancing SLM Tool Use, the NMIS GRPO Breakthrough.
So naturally, a lot of professionals are a bit skeptical about an SLM's ability to reliably use complex tools like APIs. And it's true, traditionally, SLMs fumbled this, but that was entirely because of how they were trained. A huge breakthrough from researchers at NMMIS Mumbai uses a reinforcement learning technique called GRPO, or Group Relative Policy Optimization. Instead of just blindly feeding the model more data, they built a highly specific reward system. The model gets a reward for producing valid, perfectly formed JSON. It gets a completely separate reward for choosing the exact right tool based on the user's prompt, and a third reward for using the correct parameters within that specific tool. This incredibly tight feedback loop teaches SLMs flawless, reliable tool use, almost entirely closing the gap with frontier models, and it does it without the need for endless budget-breaking fine-tuning.
And finally, part 5, Building Hybrid AI Systems, the 2026 Reference Routing Pattern.
So how do we actually wire all of this up in the real world? It's really not about choosing between SLMs and LLMs, it's about building a hybrid system. Let's walk through a standard step-by-step routing pattern. Step 1. An incoming request hits an ultra-fast, fine-tuned SLM that acts as a classifier. Step 2. For the vast majority of tasks, we're talking maybe 80% of your routine traffic, that router sends the prompt to specific SLM workers. These are your specialists that handle routine extractions and executions for absolute pennies. Then, step 3 is the fallback. Only when a task is incredibly complex, requires deep multi-step reasoning, or is just completely open-ended, does the system escalate it up to a massive frontier LLM. In this stack, your SLM is the tireless, everyday workhorse, and the LLM is your incredibly expensive, on-call expert neurosurgeon.
I think NVIDIA research really hit the nail on the head here when they recently said small language models are sufficiently powerful, inherently more suitable, and necessarily more economical for many invocations in agentic systems and are therefore the future of agentic AI. The industry consensus is just crystal clear right now. Specialized, highly optimized, and modular AI is undeniably the path forward for everyone. So I've got to leave you with this to think about. Is your agentic AI stack carrying unnecessary dead weight? Are you currently calling a massive multi-billion parameter cloud model to do the everyday work of a specialized agile SLM? It really might be time to audit your workflows, because transitioning to this hybrid approach isn't just about saving a ton of money, it's about building a faster, greener, and far more logical AI architecture for the long run. Thanks so much for joining me on this explainer, and I will catch you in the next one.